This video is on the second derivative test. The second derivative test is a way to find relative maxes and mins, or local maxima and minima. And we know already that the second derivative tells us about the concavity of the original function. So we had a different way before of finding relative maxes and mins. We would just use the first derivative, and then we would do a number line and see at any critical values, was the function increasing or decreasing before and after the critical values to determine whether that critical value happened to be a max or a min. This is a different way to find the relative maxes and mins based on both the first and the second derivative. So, the second derivative, f prime of x, tells us about the concavity of the original function. And remember that a function is concave up if the second derivative is greater than 0. It's concave down if the second derivative is less than 0. So, for example, with the function below, we would be concave down over this whole interval. We're concave down because if we look at the tangent line to the curve, that slope is decreasing. It's becoming less positive there, and it's becoming more negative there. So we're concave down over that interval. And then at some point, we switch to being concave up, maybe about here, and maybe then, so that would be an inflection point, a place where we switch from being concave down to concave up. So here we're concave up. We're concave up because the first derivative is increasing, becoming less negative and then more positive. And then over the next interval, we are concave down again. So we're concave down here, again, because the first derivative, the slope of the tangent line, is decreasing as we go over points in this interval from right to left. So this is concave down, and concave up in the middle. So let's think about that in relationship to concave down, concave down. Let's think about that in relationship to relative maxes and mins. So what's happening with relative maxes and mins when we're concave up or concave down? Well, we see that in this particular example, we have a relative max here. So this is a relative or local max. This is a relative or local min. And this is a relative max. And so we see here that we have relative maxes when we're concave down, and relative mins when we're concave up. And that makes sense because if we're concave down, that's like being at the top of the hill. So concave down, like a shape of an umbrella or something like that, top of a hill. This is a relative max right there. And if we're concave up, that's like a valley, we're going to have relative mins there. What else is occurring? Because, it's concave down over that whole interval, but it's not like all of these are relative maxima. It's just that this one point around here is a relative max. What else is happening there? Well, another thing that's happening there is that we've got a horizontal tangent line, right? F prime of x is 0. Same thing here. F prime of x is 0. And same thing here. F prime of x is 0. So this observation leads us to the second derivative test, and this is a way for finding local or relative maxima and minima. So suppose that C is a critical value or a critical number for f of x. That is a place where the first derivative equals 0 or the first derivative does not exist, where it's also the case that f double prime of C is defined, or the second derivative does exist. Then, if the second derivative is greater than 0, if we're concave up, like in this situation here, then f of x has a local minimum at the point C, f of C. And if f double prime of C is less than 0, if we're concave down, like here, then f of x has a local maximum at C, f of C. So concave down goes with local maxes, concave up goes with local mins, and these are always places where there is a critical value already, where we know that the derivative equals 0, or the first derivative equals 0, or the first derivative does not exist, like at a corner or something. So let's take a look at a quick example. So this is an example from the last video. We looked at f of x equals natural log of x squared plus 9. And for that, we took the first derivative and found that it simplified to 2x over x squared plus 9. We also took the second derivative and found that that simplified in the end to 18 minus 2x squared over x squared plus 9 squared. All right, so if we're using the second derivative test for this, so second derivative test, and we're trying to find local or relative maxes and mins, that means that we're figuring out where are places where the first derivative either equals 0 or the first derivative does not exist. So our first derivative, f prime of x, was 2x over x squared plus 9, a critical value for f, a place where that is either equal to 0 or does not exist. We see that this always exists because the denominator is always greater than 0. The something squared plus 9 is always greater than 0. So this derivative will always exist, but we can have places where this derivative is equal to 0. A fraction is equal to 0 exactly when the numerator is equal to 0. So if and only if 2x equals 0, and so x equals 0, that's the only critical number for this function. Now the second derivative test says that instead of looking at increasing and decreasing, if I already have my second derivative anyway, then I can just plug in f double prime of that critical number and see if it's positive or negative. So f double prime of 0 is 18 minus 2 times 0 squared over 0 squared plus 9 squared. So that's 18 over 9 squared over 81, and it's greater than 0. So because it's greater than 0, that means that we're concave up. So concave up, that's a shape like this, and we've got a critical value at that shape, concave up, and so that means that that point 0, f of 0, is going to be a local or relative minimum. Because from the second derivative test, if it's a critical, if x equals c is a critical value and we're concave up over that interval, then that point is a local minimum. What was that point? Natural log of x squared plus 9, so ln of 0 plus 9, 0, so the point 0 comma ln of 9 is a local min in this case. So here's an example for you to try. Use the second derivative test to find the relative maxima and minima for the function f of x equals x to the fourth over 4 minus 2x squared plus 4. So I'd encourage you to pause and try that out, and we'll talk about it in a moment. All right, so our function is f of x is x to the fourth over 4 minus 2x squared plus 4. For this, we want to find all the critical numbers for the function and then see whether the function is concave up or concave down at those points. So f prime of x, the first derivative, so that's, this is just the same thing as 1/4 times x to the fourth minus 2x squared plus 4. So using the constant multiple rule, the 1/4 just stays out front. Derivative of x to the fourth is 4x cubed minus derivative of 2x squared is 4x. Derivative of 4 is just 0. So the first derivative is just x cubed minus 4x. If we want to find the critical points or critical numbers, the places where the derivative equals 0 or does not exist, we would want to set f prime of x equals x cubed minus 4x to 0 and solve for x. We see that this is a polynomial, so that first derivative will always exist. We won't have any situations where f prime of x does not exist. So to solve that, we can factor out an x squared, and we've got x times x squared minus 4 equals 0. So we've got, we've got a critical value x equals 0, as well as x squared minus 4 equals 0, so x squared equals 4. When we take the square root of both sides, that gives us x equals 2 and x equals negative 2 as our critical numbers. Okay, so those are our 3 critical numbers. Now we want to find the second derivative, f double prime of x. So the second derivative in this case, our first derivative was x cubed minus 4x. The derivative of that is 3x squared minus 4. So that is our second derivative. And now all we care about is, at these critical numbers, is the second derivative positive or negative? So f double prime of 0 is 3 times 0 squared minus 4. That's less than 0. F double prime of negative 2 is 3 times negative 2 squared minus 4. So that's 12 minus 4. That's greater than 0. And f double prime of positive 2 is, well, it's going to give us the same thing. It's also greater than 0 because it's just 3 times positive 2 squared minus 4. So that's also going to be greater than 0. So we see that we are concave down here when at x equals 0. So concave down, that's like an umbrella. So at concave down, that's a relative or local max. So there's a relative max at x equals 0. When we are f prime of 2, that's going to be greater than 0. So we're concave up, concave up. And because we're concave up, that means that there's a relative minimum at x equals negative 2. And f double prime of 2, the second derivative at x equals 2, is also positive. So positive, concave up, holds water. The tangent line is below the curve. So this is concave up. And again, according to the second derivative test, that means we're going to have a relative minimum at x equals 2. So now we can just plug each of those values into the original function to find the relative maxes and mins. So we know that we have relative minima at x equals negative 2 and x equals positive 2. And so we want to plug into the original function. Our original function was f of x equals x to the 4th over 4 minus 2x squared plus 4. So when we plug in f of negative 2, we've got negative 2 to the 4th. That's positive 16 over 4 minus 2 times negative 2 squared, 4 plus 4. So that's 4 minus 8 plus 4. That's 0. So that means that we've got negative 2 comma 0 is one of our relative mins. And another relative min is f of 2. It looks like that's going to give us the exact same thing because this is an even function. All the x's are either squared or to the 4th power. So f of a negative value is the same as f of a positive value. So f of 2 is also 2. F of 2 is also 0. So negative 2 comma 0 and positive 2 comma 0 are the relative maxes, the relative minima of this function because we were concave up at those 2 points. And what about, so that's the relative minima, and then we have a relative max or a local max at x equals 0. So we can just plug in f of 0 is 0 to the 4th over 4, that's 0, minus 2 times 0 squared plus 4, so that's 4. And that tells us that 0 comma 4 is a relative max. So we've used the second derivative test, which really used both the first and second derivative, to find the relative minima and relative maxima for this function. Let's do one more example. Let's use the second derivative test to find the relative maxima and minima for the function f of x is 2 times the cosine of x minus the square root of 2 times x over the interval from negative pi to 3 pi over 2. So give that a shot, and we'll talk about it in a moment. All right, so we need to find both the first derivative and the second derivative. So our first derivative, derivative of 2 cosine of x, is negative 2 sine of x, minus derivative of square root of 2 times x. That's a constant times x, linear function. The derivative of that is just the slope, so negative 2. And we'll also end up needing to find the second derivative. So our second derivative, f double prime of x, is derivative of sinus cosine, so negative 2 cosine of x minus derivative of square root of 2. That's just a constant, so that derivative is just 0. So we've got our first derivative and our second derivative. We now want to find the critical numbers by finding where the first derivative either equals 0 or does not exist. So we're going to see that f prime of x exists in all cases here. So we're looking at f prime of x equal 0. Where does that occur? That occurs when negative 2 sine x minus the square root of 2 equals 0, or in other words, when negative 2 sine x equals positive square root of 2. So that's when sine of x equals square root of 2 divided by 2. So let's think about when that occurs. So remember, like with the way back to the unit circle, when we think about trig functions, there's a spot that's sort of special where sine and cosine are equal, and that's at the angle pi over 4. Back when we're doing stuff with our unit circle. So square root of 2 and square root of 2 are both the length of both of sides of that right triangle with hypotenuse 1. You could also look at a set of common values for sine and find that sine of the angle pi over 4 is square root of 2 over 2. So that's not exactly what we were looking for. We were actually looking for when sine is equal to negative square root of 2 over 2. Sorry about that. So negative 2 sine of x equals square root of 2 when sine of x is negative square root of 2 over 2, dividing both sides by negative 2. Okay, so when is that going to happen? So remember that sine, like SOHCAHTOA, sine is the opposite over the hypotenuse. So with a unit circle, sine of an angle is just the y value on the unit circle. So it's the height of that triangle. So let's think about, well, over here, if we looked at the exact same angle, this would still be sine of that angle would still be square root of 2 over 2. Would still be positive because the y value is positive. But if we look at the opposing angles over here, then we've got the same triangle where here the y value is now going to be negative square root of 2 over 2. And here as well, the y value at this point is also negative square root of 2 over 2. So let's think about what each of those angles are equal to. One way of describing this angle is to say that this angle is equal to theta equals negative pi over 4, because we were interested in all the way from negative pi up to positive 3 pi over 2. So negative pi over 4 will give us this y value of negative square root of 2 over 2. So that's one value for x that solves that equation. Another value for x that solves that equation is, if we think about this angle, that is going to be the angle theta equals negative 3 pi over 4. So theta equals negative 3 pi over 4 is also a situation where the height of that triangle on the unit circle, or the y value, is negative 2 over 2. So that's another solution to this problem. And let's see, so we were over the interval from negative pi to 3 pi over 2. Is there anything else that fits in that? Yeah, we could also go around the unit circle the other way. And so if we go in the positive direction, then we've got this value is going to be equal to, this is pi over 4, 3 pi over 4, 5 pi over 4. So theta equals 5 pi over 4 is one more value that is a solution to that equation. So we have three critical numbers. Our critical numbers are x equals negative pi over 4, x equals negative 3 pi over 4, and x equals positive 5 pi over 4. Those are the three critical values we have over the interval from negative pi up to 3 pi over 2. So now we want to plug each of those critical values into the second derivative. Our second derivative, f double prime of x, was negative 2 cosine of x. And so we're plugging in those values into cosine of x, or into negative 2 cosine of x. F double prime of negative pi over 4, that's negative 2 cosine of negative pi over 4. So let's think about what's happening to cosine at that point. So let's just draw the unit circle again. Here's our unit circle. And we know that for any triangle on the unit circle, the value of cosine is the length of the base of the triangle. So it's the x value on that triangle. And so for this angle of negative pi over 4, when we have that angle of negative pi over 4, what's going on with cosine of negative pi over 4? Cosine of negative pi over 4 is positive, so that means that this whole thing, negative 2 times that, is going to be a negative number. What about when we do f double prime of our next critical number, negative 3 pi over 4? So that's negative 2 cosine of negative 3 pi over 4. And what is that value? So negative 3 pi over 4, that is this angle right here. So this angle is negative 3 pi over 4. What's happening with the base of the triangle at that point, that x value? That's going to be a negative number. So this is less than 0, but it's times a negative, so we get a positive value. So this is greater than 0. And finally, plugging in our last critical value is 5 pi over 4. So plugging in f double prime of 5 pi over 4, well, that's actually the exact same place. So, positive 5 pi over 4 and negative 3 pi over 4 are the same. And so this is going to give us f double prime of 5 pi over 4 is also going to be greater than 0. So we see that we're concave up at x equals negative 3 pi over 4. We're also concave up when x equals 5 pi over 4. And we're concave down when x equals negative pi over 4. We're concave down here because the second derivative is negative. So that tells us concave down, remember, is looking like that. So if it's concave down, that's actually a relative max or a local max. And so that tells us that negative pi over 4, comma, whatever f of negative pi over 4 is a relative or a local max. So what is that value? F of negative pi over 4 is 2 times cosine of negative pi over 4 minus square root of 2 times x, negative pi over 4. So plugging that in is going to give us 2 times cosine of negative pi over 4 we saw above was positive square root of 2 over 2 minus square root of 2 times negative pi over 4, so plus square root of 2 times pi over 4. It's not the most beautiful number ever. We can do a little bit of canceling things out. That's square root of 2 plus square root of 2 times pi over 4. Okay, So square root of 2 plus square root of 2 times pi over 4 is a relative max, and we are also going to have relative mins at the other two critical values because we were concave up for those other two critical values. Concave up means that we are shaped like this, so we're concave up, and that means that this is a relative min. So we've got relative mins at x equals negative 3 pi over 4 and x equals positive 5 pi over 4. And we can plug in those values if we wish, or we can just leave it at that.